Today we're going to graph logs and ln's, and one of the things I want you to remember is that log and exponents are inverses of each other. So when we graph our first log function, again you probably want to hit zoom and 6 to get you back to normal. But when we hit our log equation, it's going to look a little different than the exponential. And why do they look different? Because they're inverses of each other. So when we graph a function, sometimes it's easiest to hit second graph and get some points. Get your points down where you're looking at 0, 1, 2. You can see that if I plug in anything below 1, I'll get an error. Okay, and why is that? Because if I put in 0 here, a logarithm can't be negative. So if I put in a 2, I get a 0 point. If I stick in a 3, I barely kind of go up here. You can see as x goes up, y goes up, but very slowly. And we have to come all the way down here to 11 to get exactly a 1 point, because again, if I stick in 11, I get log of 10. And what does the log of 10 mean? What should I raise 10 to get 10? And that answer would be 1. So when you graph a logarithm, it looks like on the calculator that it stops, but it doesn't stop, but it levels out, and this time it levels out vertically. So a couple different things when you graph a logarithm. It should kind of look like the inverse of our exponential. And what that means is that instead of it going forever and ever right and left, our domain this time is going to be affected. So our range is how low do we go and how far do we go up. That's going to become all reals for our logs, but our domain does not go forever and ever right and left. So our domain levels off here at x equal 1. So when we talk about our domain, we use an x variable, and it's always on this side of 1, which is greater than 1. So the graphs are going to look a little different, and the domain and range are going to be different. Okay. So let's plug in number 2 and see how things are shifted a little different. If we have the log of x minus 1, and then we have a minus 2. Remember how that affects things. It moves things around. And let's see if we can see what happens with this minus 2. What happened with the graph? It moved it down 2. So if I hit my table, I'll see how at 2 we get a negative 2. At 3, we get a negative 1 point something. So again, we're going to have kind of the basic same shape. It levels off again at x equal to 1. So our domain is x goes to the right forever, but it only goes to the left at 1. And the range on all the logarithms goes down forever. Do your little arrowhead there, and it will go up forever. It just takes a long time to get up for forever, but it's still all reals. You try number 3. It's just a little different with the natural log. Hit pause, graph, and see if your graph is what mine is. All logarithms are going to kind of have this basic same shape. It's going to go up for forever and down for forever, but it kind of stops at a particular point left and right. And how do we get that point? Just hit a second graph and see at 2 we get a 1 point. At 3, at 2 we go 1. At 3 we get a 1.6. And at 4 we're kind of going up. And again, you see here we have an error when x is equal to 1. So let's look at our graph and show how that's going to be leveling off at x equal 1. So again, you'll be asked to state the domain. X is greater than 1. Range is all reals this time. And so when you look at these logarithms, know that they're going to kind of go sideways. And if we have a logarithm, must be positive. So at x equal to -5, that'll give us a 0. But we can't go on the other side of -5. So when you graph this in here, remember you can do log the base 6 on our calculator now. How do you get to that? Hit second window and come down to the option number 5 and put in your 6. Move over here, x plus 5. Make sure you get out of the parentheses and then put your plus 3. So double check, make sure your calculator looks exactly like the function. When I graph it, it's going to kind of be a sideways, but notice it looks like it stops on this graph. But I don't want you to graph as if it stops. I want you to bring that leveling off all the way down. And how do you do that? Hit second table. The domain will be affected. The range on these logs are always all reals. Okay, so where can we get where that leveling off occurs? It's where the air is. So at -5, that's kind of where this is going to level off. At -4, we have a 1, 2, 3. We go up a little bit, up a little bit. So we graph that up and then show that you're leveling off. And again, that's a little different than what you're looking at in the graph. So you can't graph on your calculator, but you have to know that the pixels run out and that graph really continues down forever and up for forever. The domain, it only goes as far as that -5. So we say x is less than -5. So those are your new graphs for the log. Notice that your log functions look a little different. Highlight that this time the range is always equal to all reals and the domain will be affected. Okay. Problem number 5, I have another log problem, but I'm going to review some old functions. So if you will cross off number 5 and just put an old linear function here, and let's review how we do this. This is a linear function. Why is it a line? Because the x's and the y's are both to the first power. We graphed this in first semester with what was called the cover-up method. So if I cover up or make y equal to 0, x will be 3. So if I graph the point 3, 0, I'll have a point. If I cover up x or make x equal to 0, y will equal 2, and I'll have a 0, 2 point, and I'll have my line. Okay. This was standard form. Another way to do this is to solve for y and put this in the y equals mx plus b form by solving for y, and then I get y equals what? My slope is -2/3, my y-intercept is 2. This is the same thing, so my y-intercept is 2. Notice this here, a slope of -2/3 does what? Down 2n over 3, and we get to that same exact line. But if you know standard form, you can get to that line a lot quicker. So I'm going to refresh that, and if you'll add a 6 equation in your notes, I want to remember what a quadratic function looks like. So if we have a 2x squared minus, let's say 5x plus 2. Let's see, this is a quadratic. What does a x squared look like? You should remember it's a parabola, so it's a u. If the letter in front, the number in front is positive, we should have an up parabola. So again, these are just some old review problems. Let's go back to our graphing this on our calculator. We should kind of have in a mind's eye what it will look like. How do I get that u? I can kind of sketch it in there. again, probably the best thing to do is go to the table and get some points. Let's see where the U, 0, 1, 2, 3 are some pretty good points there. So when I go to the second table, 0, 1, 2, 0 is at a 2, 1 is at a -1, 2 is at a 0, 3 is at a 5. And so when I'm looking at these points and my graph, I can kind of see in here how this is going to turn into a U, and that's how I want you to graph your parabola. Okay. Again, you can hit just trace and go to the 0 point and get 2. You can go to a 1 point and get -1, a 2 point. That's another way that you can get just some points or hit that second table. So I'm going to have you graph today. Ask some questions. You have to become familiar with your log. If I ask you domain and range of a parabola, domain goes for ever and ever right, ever and ever left, so that would be all reals. But let's look how low this parabola goes and how high it goes. So it looks like it goes for forever. How low does it go? If I trace down here and get to this low point, it looks like it goes, about -1. So no matter what, y is above -1.12. And that's how we'd say the domain and range for a parabola.